17c, here's an example of finding the solution to a linear system of differential equations with initial conditions 0, x of 0 equals 4 and y of 0 equals 8. The equation is dx dt equals 5x plus y, dy dt equals negative 7x minus 3y. And the way we're going to solve this is the usual way. We're going to find the eigenvalues and find the eigenvectors. I'm going to erase that because it's on the other side of the board. We'll get to it in a minute. So eigenvalues, our matrix A is 5, 1, negative 7, negative 3. So we've got 5 minus lambda, 1, negative 7, minus 3, minus lambda. Taking the determinant of that, we're getting 5 minus lambda, ooh, that's great looking, times negative 3 minus lambda, minus 1 times negative 7, equal to 0. So we got, let's see, negative lambda times negative lambda is lambda squared, plus 3 lambda minus 5 lambda is minus 2 lambda, and then minus 15 plus 7 is minus 8, 0. Factoring that, we get lambda minus 4 times lambda plus 2, equal to 0. So we've got lambda 1 equal to 4, and lambda 2 equal to negative 2. For lambda 1 equal to 4, let's find the eigenvectors. I'll take my matrix A, 5, 1, negative 7, negative 3, right? This is A minus lambda I. This is just A, 5, 1, negative 7, negative 3. Multiply it by the candidate for the eigenvector, which I don't want to use x and y because it's going to get confused. Let's just call it A and B. Why not? Equals 4. Using the first equation, 5 times A plus 1 times B equals 4 times A. Subtracting 5A, B equals negative A, let A equal 1, B equals negative 1. So the eigenvector V1 is 1, negative 1. Which makes sense, right? So you multiply 5, this times 1, negative 1, you get 5 minus 1, which is 4 times 1. If you let this be 1, negative 1, negative 7 times 1 is negative 7, minus 3 times negative 1 is positive 3, and negative 7 plus 3 is negative 4, equals 4 times negative 1. From lambda 2 equal to negative 2, same deal. 5, 1, negative 7, negative 3 times AB equals negative 2 times AB. Again, using the first equation, 5 times A plus 1 times B. My A is dumb, they look at 9s. 5A plus B equals negative 2A. B equals negative 7A. Let A equal 1. B equal to negative 7. So V2 is 1, negative 7. So those are our eigenvectors. Going with our eigenvalues, this pen seems to be dying. So then going to the other side, the general solution is xy equal to c1 e to the lambda 1 t times v1. That's what this is here. c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2. This pen's also trash. See if any of my pens are a big one. So the only thing we have to do now is find c1 and c2 by plugging in x sub 0 equals 4 and y sub 0 equals 8, or y at 0. So what I'm doing is I'm saying, right, so xy at 0, so 4, 8 equals c1, e to the 0 is just 1, c2 e to the 0 is just 1. So what we end up with, besides pens that are trash, we get 4 equal to c1 times 1 plus c2 times 1. So 4 equals c1 plus c2. And 8 equals c1 times negative 1 plus c2 times negative 7. And then you can solve, like you can solve for c1, or you can just add these together. Adding them together, you get 12 equal to c2 minus 7 c2 is negative 6 c2. So c2 equals negative 2, and c1 equals, let's see, c1's got to be 6, right, if c2 is negative 2. So for these initial conditions, our actual final equation, or our particular solution here, I'm going to erase this, is xy equal to, good pen in the house. Oh, that's my good red pen. xy equal to c1 e to the forward c1 negative 1 plus c2 c2 is negative 2 e to the negative 2t times 1 negative 7. And since our eigenvalues are opposite signs, right, we have a positive eigenvalue and a negative eigenvalue, it means we have a saddle, and it's unstable because as t goes to infinity, this part, right, e to the negative infinity is going to go to 0, but this part here is going to get really, really big, right? This part's going to blow up to infinity. So this thing is going to, right, this thing is unstable near the equilibrium. It's going to go away from it. And again, you could put this into p-plane and see that you have a saddle. The one other thing I will say is if you have this initial condition, things are slightly different. It's kind of interesting. So notably, this initial condition is actually a multiple of this eigenvector. What we're going to end up getting is we're going to end up getting c1 is 0 and c2 is not 0. Check it out. So if I plug in this, I do, right, 2, negative 14. Right, so setting t equal to 0, I get c1, right, I get the same thing. c1 times 1 negative 1 plus c2 times 1 negative 7. So I get 2 equal to c1 plus c2. I get negative 14 equal to negative c1 minus 7c2. And when I add these together, I get, let's see, 2 plus negative 14 is negative 12. C plus negative c1 is 0. And c2 plus negative 7c2 is negative 6c2. So I get c2 equal to 2. If c2 is 2, c1 is 0. So in this situation here, my particular solution, xy, looks like, well, c1 is 0, so I don't get any of this part here. I just get c2, which is 2, times e to the negative 2t times 1 negative 7. So in this particular case, when you're starting on a point that's already on the eigenvector that goes with the negative eigenvalue, in this particular case, you're going to be stable because you're traveling along this line of stability that takes you towards the origin. And again, as t goes to infinity, this is going to go to 0, and you're going to get 2 times 0 times 1 thing, so you're going to get 0, 0. So for this particular initial condition, it would be stable going towards the origin on the one line of the saddle that actually goes directly into the origin. But any other initial condition that doesn't start on that line shoots you off somewhere else. And again, look at p-plane, it'll help you kind of see what's happening.